Hello everyone, in this video we are going to talk about another group of compound called nitrile. So nitrile have a functional group that is the carbon-nitrogen triple bond. And the nitrile actually can consider as a carboxylic acid derivatives. So the reason why is you have this carbon and you have the pi bond between carbon and a electron negative item, which here is a nitrogen instead of oxygen, but it will undergo very similar reaction as the other carbonyl compound. So that's why nitrile is considered as a carboxylic acid derivative. So because we have this carbon-nitrogen triple bond, the first thing what we can think about is when we shoot this molecule inside our spectrum, we are going to expect to see the carbon-nitrogen triple bond stretching that is between 2100 to 2300 with numbers. So that is a very, very signature peak in the IR. And for the mass spec, because we have this nitrogen, we are going to follow the nitrogen rule that if you have all the number of nitrogen, the M plus peak, this mass to charge ratio is always an odd number. So that is some features for the nitrile. And for the nitrile, we are going to first look at how to name it. So here it's called nitrile. So basically we are going to end this naming by nitrile. And how to name it, the carbon that have this triple bond will label as 1, and we are going to keep labeling and counting. So on this main group we have, on the main parent chain carbon chain, we have 4 carbons. So that is the butane. Okay. And then we're going to just put the name nitrile. So that is butane nitrile, for example. And a very common solvent we use in the organic lab is called acetone nitrile. So it's this molecule right here. So acetone nitrile, I'm going to spread this out first, nitrile. So when we were talking about SN2 reaction prefer to have polar aprotic solvent, and the nitrile is one of them that is commonly used in the lab. So when you have the nitrile, sometimes nitrile has to be considered as a substituent on the parent chain because it does not have as high priority as carboxylic acid. So if you have a same group on a carboxylic acid, then carboxylic acid will win. So nitrile will just act as a substituent. So when it is substituent, we call it a subinyl. And one example we saw this substituent before is when we have a ketone that we react this ketone with potassium cyanide with the presence of the acid. So what we are going to have here is the formation of cyanohydrin. So that is a good example, cyano as a substituent. So that is how we name nitrile. And more importantly, we want to know how to prepare it. So how to prepare it? We have a reaction, is SN2 reaction, preparation of nitrile. And through SN2 reaction and C and the cyanide, this group is very, very nucleophilic. So if we have a primary alkyl halide and we throw in, for example, potassium cyanide, what we are going to have is this nitrile. And the beauty of this reaction here is if you start with 3 carbon, you are going to end up with 4. So that increases the number of carbon chain. But because all in all, this cyanide, it is a carbon-based nucleophile. that is increasing the carbon number on the carbon chain. So that is how we prepare it. So far, that is the reaction we have learned so far to prepare nitrile. So the next, I'm going to just write out another reaction that also will make the nitrile, and we will learn this reaction in the later chapters. So if we start with amide, and amide can also go to nitrile, that if we use a cycle 2, and that will do the job. So you start with 2 carbons and 1 nitrogen. Now you still have 2 carbon with nitrogen. And the side product here is sulfur dioxide with 2 equivalent of HCl. So we're not going to talk about this reaction at this moment yet. So we're not going to go into the detail about reaction mechanism, but that is one way that you can also make a cyanide. So at this moment, this reaction SN2 reaction to react with alkyl halide will be the one that you need to focus on. So that is how we prepare nitrile. So the next thing is we're going to talk about what nitrile can do. In other words, what is the reaction that nitrile can undergo? So not a lot. The first reaction nitrile can undergo is hydrolysis. So earlier when we were talking about synthesis of carboxylic acid, there are one reaction that can lead to the carboxylic acid by hydrolysis reaction of the nitrile. So for hydrolysis of nitrile, there are 2 conditions. The first condition is acidic condition. So basically in this reaction, we do have the proton source. And let's write out this reaction. So we have our nitrile, and we are going to have acidic condition. So for example, what we have here is hydronium. Because of hydrolysis, we do need to have the water source. So we can put the heat there. And the end product is to have our carboxylic acid. So that is the first way we can make carboxylic acid by hydrolysis of nitrile. And for this reaction, the reaction mechanism is rather complicated. So I'm not going to introduce the reaction mechanism yet in this video. So just as you know, the hydrolysis under acidic condition will lead to a carboxylic acid. And the next condition here is basic condition. So again, we are still looking at start with our nitrile, and then now this time we are going to have 2 steps. The first step, we are going to use the basic condition. So we need water, because hydrolysis, we need water. And also we need to have the base, so sodium hydroxide. And after you have this base, after hydrolysis, you form a carboxylic acid, that will not stay. You are going to have as the carboxylate. So the second step is we are going to introduce the proton source to protonate it back to carboxylic acid. So that is the hydrolysis under basic condition. So for this reaction, the reaction mechanism is a little easier, but we are not going to talk about in this video as well. So that is the first reaction. The second reaction that the nitrile can undergo is to react with Grignard reagent. Since Grignard reagent is carbon-based reagent, so what we are trying to do here is we are going to add more carbons. So for example, we have this nitrile, so this is ether nitrile, and we are going to put Grignard reagent. For example, this Grignard reagent, and then second we are going to use a proton source. You can use water or you can use a hydronium. So basically we need here is the proton source, and the outcome of this reaction is we are going to add 2 more carbons that are from the Grignard reagent. So if I highlight these 2 carbons, right here, 1 and 2 is the one that's added to this main carbon chain. So from 2 carbon, now we have 4 carbons. So your question might be that why stop at the ketone and it cannot keep going to form a alcohol? So the reason for this is for this reaction mechanism that we are going to form an imine in the process. So what will happen is this carbon will be attacked by our Grignard reagent, and at the same time pi bond move over. So that first step, what we are going to achieve here is carbon nitrogen double bond with the lone pairs on this nitrogen with a negative charge, and that 2 carbon, the ethyl group will be added, the 1 and 2 carbons. And then after that, because we have the proton source right here, when you have this negative charge on the nitrogen, so what it will do is need to get rid of it by protonation. So what we will have here is this molecule. So this molecule is imine, as we learned earlier, when the aldehyde or ketone react with the primary amine, and after the process of removing the water, imine will be the product. So when you have the imine and you have the aqueous acidic condition, so what would happen here is the next imine actually will undergo a hydrolysis. So when imine undergo the hydrolysis, basically what we are going to have here is this bond basically is gone, and it will be replaced by the carbon-oxygen double bond. So this is a hydrolysis step of imine in order to achieve our final product. So that is why you will not have a alcohol made in this process, in this reaction. So with Grignard reagent with the nitrile, you are going to end up at the ketone or aldehyde at this moment. So that is with Grignard reagent. The last reaction I'm going to just right at the corner here, that we are going to reduce the nitrile. So if you have nitrile, and first we are going to use this super aggressive lithium aluminum hydride, and then at the end what we are going to have here is water. Okay, so with this very aggressive reducing reagent, so all the pi bond is added by hydrogen, and what we will have here is amine. So the nitrile will be reduced to the amine, and it's primary amine. So I want to point out here is this water is needed, and we do not use the hydronium. The reason is why is the amine is the base. If you have hydronium, what you are going to end up with here is, if this is hydronium, you are going to end up with ammonium around here. So we want amine, so we are going to introduce a neutral condition to provide that proton source. So that is further reduction. So the nitrile can also undergo a partial reduction by using a bulky hydride, that is our dibol H. So in the past we learned dibol H is a sterically hindered hydride and can react with the ester. So here it also can react with nitrile with very similar condition. Most of the time you do need to run this reaction at a very low temperature, and what we'll do is, just as ester, it will go only to the aldehyde and cannot be further reduced by the dibol H for the reduction. So that is the reactions that nitrile can do. So that is the end of this video.